So I mentioned that if we increase the concentration of the base, we're going to actually change from a unimolecular elimination to a bimolecular elimination. We know the rate for each elimination depends on the concentration of the base. So by increasing the concentration of the base, we can increase the likelihood that the bimolecular pathway will dominate. Given that an increased concentration of the base is going to have no effect on the rate of the one pathway. So if we were to take that secondary substrate that we were working with and our triplet, the triplet derived from 2-pentanol, and we were to react this with sodium hydroxide with 10 equivalents, of sodium hydroxide as opposed to 1 equivalent of sodium hydroxide, we would now actually see bimolecular reaction. We would observe second order kinetics. And we would still get predominantly the Saytzeff product. And not very much. Of the Hoffman product. And we would again still get mostly the trans and not as much of the cis. And we'd see very little substitution reaction. We would probably get some substitution reaction, and if we were to run this in GMSO, maybe we could get a little bit more substitution reaction. But as we know, when we work with a secondary substrate, the SN2 reaction rate is slowed, and since we have a hard base here with hydroxide, we might expect elimination to be the dominant pathway rather than substitution. So what's the mechanism of the E2 elimination? Because in addition to the regioselectivity, we said that the E2 elimination is a stereospecific reaction. So to look at this mechanism, it's going to be more convenient to have our leaving group in the plane of the board. So I'm going to rotate it so that my leaving group is actually in the plane of the board. And I have the hydrogen and the methyl group out of the plane. So we need to make sure we keep our stereochemistry the same when we do that rotation. When I rotate this to go into this position, the hydrogen is going to take the place of the triplet, and the methyl group is going to come out. And if we were to look at that, we would determine that this is an R stereocenter, with the oxygen taking priority, then the carbon that's attached to another carbon taking priority over the methyl group. Right? So that's an R stereocenter. Hopefully you can see that it's an R stereocenter here as well, and this time you need to put yourself behind the board and looking this way and going from the triplet, which is out in front of you, like this, that is also an R stereocenter. The other thing I need to do is I need to have a hydrogen on the beta carbon, but also in the plane of the board. So I'm going to rotate it so that that hydrogen is there, and I've got my other hydrogen and my ethyl group in the dashed wedge structure. pi bond, and that's why it's convenient to have the hydrogen that's being removed and the leaving group both in the plane of the board, and the leaving group is going to be kicked off simultaneously. So all three of those things are happening together. I will have a single transition state, which will now have a partial bond to the hydrogen that's being removed and a partial bond to the carbon that is being removed from. I've got a partial pi bond here, and I've got a partial bond to my leaving group. Partial negative on the oxygen, partial negative on this oxygen. I've still got my hydrogen going back. I've got my CH3 group coming up. So my transition state looks like that. It's a single step, it's inserted. Bond breaking and bond forming occur simultaneously, and I have a partial pi bond in my transition state. You'll notice that the way I rotated this to have this one hydrogen here and have the ethyl group in the back and the hydrogen in the front, I have my CH3 and my ethyl, my CH2CH3 group, methyl and ethyl group on opposite sides, which means that when I finish this process, I will end up with the trans stereochemistry, right? These two hydrogens on the opposite side of the double bond, and the CH3 and the ethyl group also on opposite sides of the double bond. Hydrogen is in the plate of the board, which would then put the ethyl group here. And I get the cis stereochemistry. But there's going to be less steric hindrance having the methyl group and the CH2CH3 group on opposite sides of one another in that transition state. And that's going to cause this to be the most stable transition state possible. Again, the partial pi bond here likes to be more substituted, which makes this primarily the Saytzeff product rather than taking off one of the hydrogens from the methyl group, where you would have a less substituted partial pi bond in your transition state. This is what we refer to as an anti-elimination. The hydrogen that's removed from the beta carbon has to be what we call anti-periplanar to the leaving group. So it's got to be in the same plane, because the two p orbitals that are forming have to be at an overlap to form the partial pi bond, and it has to be in an anti-conformation. So if I were to draw this as a Newman projection, and this starting material on my back carbon, this is going to be the back carbon, I have the triplet coming down. Methyl group off to the right, hydrogen off to the left, and then on my front carbon I have the ethyl group off to the left, the hydrogen on the right, and the hydrogen that is being removed pointing up. The hydroxide is taking that hydrogen off, pushing this pair of electrons in to form the pi bond, and kicking out the triplet, and you'll notice that there's no uncomfortable gauche interaction between the methyl group on the back carbon and the ethyl group on the front carbon, anti-position. And it must be anti-elimination through a single transition state with an energy diagram that looks very similar to the energy diagram for an SO2 reaction. Just a single step. Usually a pretty exothermic reaction, because the reaction of hydroxide with hydrogen to form water forms a very strong OH bond. So why does it have to be anti? Why can it not be a syn elimination? Why does the hydrogen have to be in an anti-position and not eclipsed? Certainly, the eclipse conformer would be less thermodynamically stable, but there is free rotation. The eclipse conformer is possible. Why does it have to be in an anti-position? To understand that, we need to look at the orbitals involved in the reaction. And specifically, we need to look at the LUMO that's associated with the carbon to leaving group bond. I'm going to use a simpler example to talk about this. We're just going to use bromoethane and we're going to have a base. Removing that, we're going to use the tertiary butoxide ion in this case. Which is a very strong and very hard base. This is going to take this hydrogen off, create a pi bond, and take off the bromide. The LUMO orbital, which is the orbital you need to donate electron density into if you want to break that carbon-bromine bond, has a large lobe here. And when we talked about why the SN2 reaction has to go with inversion of stereochemistry, we said it's because the LUMO orbital is here on the opposite side to where the bromine is, and the nucleophile is going to want to come in and attack. The bond that's being broken here is a bonding orbital between this carbon and hydrogen that looks like this. So the sigma bond you're breaking has its largest lobe over here where this hydrogen is, and only a fairly small lobe over there, right, from the back end of the sp3 hybrid orbital. This large lobe here that has the electrons in it prefers to interact with the large lobe of the LUMO orbital where the electrons are going. So you get favorable orbital overlap here. One of the principles of molecular orbital theory, remember, is that orbitals prefer to interact with other orbitals of similar size. The largest lobe of the anti-bonding orbital is away from the bromine. The largest lobe of the bonding orbital is towards the hydrogen, right? There's only a fairly small lobe over there. So if we were to try to do a syn elimination, we would be working with the same LUMO orbital, which is mostly over here. But now the orbital that's breaking, where the electrons are, only has a comparatively small lobe on this side. Much less favorable interaction of this small lobe with the large lobe of the LUMO. Than here where we have a more similar orbital size overlap. We don't get as much constructive interference, which makes that partial pi bond that we're forming in the transition state much less favorable. It's essential that this orbital be coplanar with the LUMO orbital, because otherwise we can't form a partial pi bond at all. If we were not coplanar, we would be looking at a Newman projection where the bond that we're breaking to the hydrogen through this LUMO orbital is in one place, and the bond that's breaking to the leaving group, oops, sorry, I forgot, I switched to bromide. And the bond that's breaking to the leaving group, right, the LUMO orbital would be here. Those two orbitals don't have the same symmetry, which means that no interaction is possible. essential to stabilizing the transition state and making that bimolecular pathway favorable in the first place. Another complicating factor for the E2 elimination is that if we switch the base from a strong unhindered base to a strong hindered base, getting ahead of myself, we will actually get the Hoffman product instead. So if we go back to our original triplet, if we treat this with sodium hydroxide or sodium F oxide, we get primarily the Saytzeff product. Which is now a sterically hindered base. Instead of getting the Saytzeff product as our predominant product, I'll actually get the less substituted alkene, the Hoffman product. Sterically, the hydrogen's attached to the methyl group here because we don't have that additional blocking group preventing the approach of the sterically hindered base. So the sterically hindered base, T-butoxide, is going to take off the most accessible hydrogen. Rather than the hydrogen that leads to the more stable product. If we look at the energy diagram, what we have is a situation where the more stable Saytzeff product has the higher activation energy. So the Hoffman product has the lower activation energy because of the more accessible hydrogen and is the kinetically favored product. Whereas the Saytzeff product is the more stable and therefore the thermodynamic product. In the case of the E1 elimination reaction, which is often all in equilibrium, the Saytzeff product will always dominate. Because if you have an equilibrium reaction, you will form the more stable material because all activation energy barriers can be exceeded. In the case where you don't have enough activation energy to go over that larger hump to get to the Saytzeff product, the Hoffman product will dominate. And we need to consider the transition state that leads to the Hoffman product versus the transition state that leads to the Saytzeff product to understand why there's this energy gap between the two. And the best way to do that is going to be with Newman projections. So we have our triplet, and we had our CH3 group and our hydrogen, and we had our CH3, CH2 group here, and our hydrogen it's going to get something of an interaction with that methyl group. Right? There's going to be some steric hindrance there, whereas if we look at the transition state that leads to the other product, and again, I'm going to have to rotate this so that I get this triplet group to be in the plane of the board. So I'm going to rotate, redraw that molecule by moving the triplet into the plane. If I move the triplet into the plane of the board, this hydrogen is going to stay in front, and this other group, this propyl group, is going to stay in the back. And then I can look at the Newman projection of that. Here, over here on the right, and then the hydrogen is being moved is here. Butoxide coming in to attack this. So there's no additional group on the same carbon like there is here. Here we have an additional group on the same carbon if I were to actually write that. T-butoxide group is going to be doing some interaction with this group that's on the same carbon, these adjacent hydrogens here, as well as the gauche interaction there. Here we have only the gauche interaction here with this other alkyl group, but we don't have any additional hindrance of T-butoxide interfering with another substituent on the same carbon. So there's less steric hindrance here than there is for approach here. And thus, with a strong hindered base, we're going to remove the more accessible hydrogen. This transition state will have a lower energy, steric interaction. When you see T-butoxide, T-butoxide always goes by an E2. And when you see lithium diisopropylamide, you will also always know that that is one of the strong hindered bases. Lithium diisopropylamide. Which has the abbreviation LDA. Always is a strong hindered base that deals in E2 elimination with Hoffman regiochemistry. And potassium T-butoxide is the other one that when you see it, you'll know that they go E2 with Hoffman regiochemistry. And that is the conclusion of our discussion of substitution and elimination reactions. All that remains is to walk through a series of reactions and analyze which of the pathways is likely to dominate for which of those reactions. And then there'll be lots of practice so you get used to being able to identify which pathway is going to be the most important pathway in every given